Hi everybody, Mr. Lee here, and in this video we're going to go over the kinematic equations. The kinematic equations are used to describe moving objects, but more specifically moving objects that have a constant acceleration. These equations can be used either here on Earth, on the moon, or anywhere in the universe, and the equations still hold true. It's a very cool thing. Alright, so on the screen you see the three kinematic equations. I'm going to go over how to read these equations, and I'm going to go over some tips and tricks in order to how to solve kinematic type problems. We will get into two-dimensional problems in a little bit, but for now we're going to stick with one dimension. So what that means is an object is just moving either forward and back, left and right, up and down, okay? Only in one of those axes. So let's begin. So this first equation that you see here, sometimes you might see me write this equation in the following form. Instead of saying v sub x, I will write v final. Now this x just means that it's in the x-axis, and sometimes it could be in the x-axis, sometimes it could be in the y-axis, but the equation sheet that College Board gives us has it in the x-axis. So v final is equal to v initial, so we see that it's vx0. Right? So it's just v sub initial plus the acceleration times the time. Now, because we are using equations with variables, notice that my t's, I don't know if you picked this up, but my t's have this tiny little tail. And that's so that when I write the addition sign or the plus sign, it helps me better differentiate the addition sign from the t, which is the time variable. All right. So here we have final velocity, initial velocity, acceleration, and time. So this is the equation that we can use in order to solve for either the final velocity, the initial velocity, the acceleration, or the time. All right, next one. So this next one, you will see me write it as x sub f is equal to x sub 0 plus v initial times the time plus 1/2 times the acceleration times the time squared. Now, a couple of things here. There's a lot going on. So each one of these is a variable. So this xo is a singular variable, so that's the initial position. This is the initial velocity, and this is the time. We read these as two separate variables. This isn't one giant one. Okay, and next, the one thing that I find a lot of students do, that they make this mistake, is they look at this 1/2 at squared, I'll write it over on the side, and they rewrite this for whatever reason like so. And this is not the case. Okay, what is going on here is you're not squaring the entire thing, but rather only that time variable is squared. All right, and this last one, this is the final velocity squared, is equal to the initial velocity squared plus 2 times the acceleration, all times this is x final minus x initial, which we also know to be as the displacement equation. Okay, and these three equations, if you rearrange them, they come from the equations that we already came up with, such as delta x is equal to x final minus x initial, right? And we did the velocity equation. We said the velocity is the displacement over time. And we also said that the acceleration is equal to the change in velocity over the change in time. Okay, and we also rewrote this to be the displacement over time, all over time, right? So with these equations, we could come up with these three equations. Now, the next thing I'm going to go into is when you're given a kinematics problem to solve. Okay, when you're given a kinematics problem to solve, there is a certain strategy that I like to use in order to help solve it. And this is what we call the kinematics table. All right, so what I'm going to do is I'm going to show you the table, and I'm going to add a couple of different highlights for this table. Now, trust me when I say, whenever I personally solve any kinematics problem, I always start off by writing out these tables. It's just a great way for you to focus on what's important, what the problem gives you, and what you need to solve for. So I like to start off with the position variables. So x initial, x final. Then I like to go to the velocity variables. Velocity initial, velocity final, the acceleration, and then the time. And I like to create this as a table, like so. And then based on what the problem gives you in terms of numbers, I like to fill in that table to see exactly what we need in order to solve it. Now, with this strategy, it really helps because we have three equations, right? So let's go back to these three equations. We have these three equations, and you just might be wondering to yourself, when do I use which equation? Because, like, you know, it could be any one of those three. But trust me when I say, if you come up with this table, it really helps when it comes with the problem-solving aspect of the kinematics portion. Alright, so here we have a classic kinematics problem, an airplane that is accelerating down a runway. Okay, so we have an airplane that accelerates down a runway at 3.2 meters per second squared for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. Alright, a couple of strategies. One, I like to highlight any piece of information that they give you with numbers and units. So the first one is the 3.2 meters per second squared. Okay, so highlighting that, and not only am I highlighting it, I'm going to write down what that tells us. Okay, if it's meters per second squared, that tells us the acceleration. Next, 32.8 seconds. Okay, units seconds, that tells us the time. Until it finally lifts off the ground. Determine the distance traveled before takeoff. Now, usually what happens here is students usually stop underlining or highlighting all the important pieces of information, but right there, the thing that you are solving for, the unknown, is actually a very important piece of information. That tells you exactly why you're solving this problem. So I'm going to also highlight that. Determine the distance. Okay, what is this? So this is a D. I'm just going to say X final. Okay, just to keep it in line with this table. All right, so I have my three equations. I have my table. Next, what I'm going to do is I'm going to fill in this table. Now, I'm going to add some couple of caveats here and there because there's a lot about this problem where they don't really give you the information. You kind of have to read between the lines. Okay, so do they tell us the initial position? And the answer is no. A lot of the times, problems won't give you the initial position, but you should be able to conclude that if they don't give it to you and you're not looking for it, the initial position is 0. Okay? Because that's where you start. That's where you start to measure, at 0. Right? We are looking for X final. Now, see what I do here. I'm going to put a question mark there because that's what you're looking for. Okay? I like to do that because it's a visual reminder that that is a given piece of information. That given piece of information states that you are looking for it. The initial velocity. All right, so they don't tell you how fast initially the plane was going, but you would assume that this plane would start from rest. So that would be 0 meters per second. The final velocity, do they tell us that? No, they don't tell us that, so I'm going to leave that blank. The acceleration, they do tell us, 3.2 meters per second squared. And the time was 32.8 seconds. All right, so we have our table. Okay, sometimes I know people like to do a little sketch. Okay, and I do recommend that you do some sketches. So this is my plane. Right, those are the plane's wheels. I don't know why it's in the back. And this plane travels for a well, we don't know, right? We don't know the X final, so I'm going to put that up as a question mark. We know that the time is 32.8 seconds, and we know that the plane has an acceleration for 3.20 meters per second squared. The initial position is 0 meters, and the initial velocity is also 0 meters per second, right? All right. Now, was this picture necessary? No, but it definitely helps me get my thoughts down onto the paper so that it can help me solve the problem. All right, next, you have to take a look at these three equations. Now, I do not know which of these three equations that I have to use in order to solve for this problem, okay? I am honest when I say I don't know. So I have a strategy. What I do is I take my table and I ask myself, do I have this piece of information? Okay, just like this. I take a look up here. This is v sub f. Do I have the final velocity? I take a look at my table. The answer is no. I don't have the final velocity. Okay. Do I have the initial velocity? I do have the initial velocity. Do I have the acceleration? I do have the acceleration. Do I have the time? I do have the time. Does it have the one variable that I am looking for, xf? It does not have xf, so I could skip that equation. I don't need this one. Okay, I don't need that equation. Next one. Do I have position final? I do have position final. Okay, now you might be telling yourself, Mr. Lee, you don't have that number. You're looking for it. Well, remember what I said. The unknown piece of information is a given piece of information. Okay, what you're looking for is something that is given. So yes, I have that piece of information. Do I have my initial position? I do have my initial position. Do I have my initial velocity? I do have my initial velocity. Do I have the acceleration? I do have my acceleration. Do I have the time? I do have the time. Now, you can use the equation when you are missing all but that one variable that you are looking for. And in this case, it's the final position. So I'm going to use equation 2. All right. So I suggest, and please do this, that you write the equation down without any variables at all. Okay? Do this with no variables at all. All right. Next, what I want you to do is I want you to, if there's any zeros involved, okay, put those zeros in. And this will just like kind of clean things up. Now notice how I said only the zeros. x0, that's a 0, okay, plus initial velocity times time. Initial velocity is 0, so 0 times time, which gives us 0 by the way, plus 1/2 a t squared. Right? Now I'm going to get my red ink to show you why this cleans up so easily. Anything with the 0 we can get rid of. 0 times time gives us 0. Get rid of that. So what this gives us here is a way to rewrite this formula. And we just clean things up a bit. All right. Now, at this moment, you should be able to rearrange the equation to make it into the form for what you are looking for. Luckily for us, we're looking for final position, so we don't have to do any rearranging. But a little side note, if you were looking for, let's say, the acceleration variable, I'll just do a little side lesson here. If I was looking for acceleration, I would rearrange this equation so that it would be a is equal to, okay? And I'll do it just like this. I have 1/2 here, so I want to get rid of that 1/2. I'm going to multiply both sides by 2. So I get 2xf is equal to at squared, because the 2 in the numerator cancels out with the 2 in the denominator. Okay. I still want to isolate this a. So we have t squared here. In order to get rid of this t squared, I'm going to divide both sides by t squared. Okay. And this allows us to have a t squared in the numerator and a t squared in the denominator. So cancel that out. Right. And this leaves us with 2xf over t squared is equal to a. Okay, so I have isolated the acceleration variable. So if I was looking for acceleration, I would just use this form. And the reason why I'm telling you this is because a lot of times on the AP exam, they will give you problems, these kinds of problems, without giving you any numbers. And then they'll ask you to derive an equation that could help you find the unknown variable. So if this problem was like, what is the acceleration? Derive an equation for the acceleration. We would do that by going through this process. Okay. Now, if you want to clean things up a bit, we could do that a is equal to 2 times the final position over t squared, right? And that will be our final answer for the acceleration. Okay, so that's a little side lesson. Let's go back to the main problem here. We want to know the final position. All right, so at this moment, once you have isolated the one variable that you're looking for. Now, trust me when I say this, now enter your numbers. And once again, this is just good practice because a lot of the times on the AP exam, they do not give you numbers to mess around with. So this is just good habit. All right. I'm putting in my 3.2 for deceleration, and my time is 32.8. I'm going to square that. All right. Remember, the time is the only variable that is squared. And at this moment, I'm going to get my handy dandy calculator. All right. So we have 32.8 squared. So I'm just going to multiply that by itself. 32.8. Okay. Times 3.2 times 0.5. And that gives us an answer of 1,721.344 meters. 1,721.344 meters. Okay. Let me just double check that I did that right. 1,721.344 meters. Very good. All right. Now, at this moment, I'm just here to tell you that you don't have to go out to 3 decimal places. Either 2 or 3 is fine. So I would take that or this as a answer. Okay. And that's just a good way for us to respect the amount of significant digits that you would normally see. So 2 decimal places. Okay. All right, so that's our first problem. In the next video, I'm going to do a couple more where we can see how we can use the other 3 equations. I'm going to go over the same process. I'm going to draw out my table. I'm going to sketch it out, and I'm going to isolate the variable, and I'm going to finally solve. Remember, solving is the very last thing. Anyways, I can't wait to see you then. This is Mr. Lee with the Kinematics video. Bye-bye.